Okay. All right. So on Friday, we looked at alpha, beta, and gamma in terms of how we could determine what kind we had based on charge and motion. Okay. There's another way we can tell based on what they penetrate. Okay. So based on what they're built of, they're going to penetrate to different amounts. So the first ones they found, alpha particles. Okay, they're big and they've got a big charge, a big positive charge. So if an alpha particle comes shooting at another atom, it's more likely to run into it because it's big. Okay. It's more likely to be stopped by it because the positive nucleus is going to be pushed by the positive nucleus of the other atom. Okay. So it'll be pushed back. Okay. So they don't penetrate very far. They're stopped by your skin. They're stopped by paper. So the danger is that this alpha particle is going to hit one of your living cells, and it's going to hit some part and knock it off, and it could kill that cell. If it's the DNA, it can knock the DNA around. The DNA has repair mechanisms. If it's repaired, life's okay. If it's messed up too bad, the cell dies. But if it's messed up just enough, and the cell repair mechanism comes to fix it, DNA repair mechanism comes to fix it, and fixes it wrong, you've got a chance of cancer. Okay, you got a chance. Okay? So every time you get hit with an alpha particle and messed up your DNA, you got a chance of getting cancer. The more times you get hit, the more likely that cancer is to stick. Does that make sense? It's going to mess up that cell. The cell's going to make some proteins. Your immune system may not identify those proteins. So if the immune system can't identify this cell that's growing out of control, then the cell gets to keep growing out of control. So it can cause skin cancer because it can hit your skin. It can cause lung cancer if inhaled. In California, before you can sell a house, you have to get a termite inspection, because termites are a hidden danger that nobody can see, so you always have to get a termite inspection before you can sell a house in California. Just not here, what you're saying. Okay, so, but in Michigan, you don't have to get a termite inspection because there's no termites. Okay. Well, instead, you have to get a radon inspection. So radon is a colorless, odorless gas that's more dense than air and is radioactive. So we talked about radium undergoing alpha decay, and it makes radon. Well, radon is also radioactive, and it goes through alpha decay too. But the danger is that you're going to breathe the radon, and then the alpha decay is going to happen inside your lungs. Okay? So that's how it can cause lung cancer, is you breathe it in, causes cancer inside your lungs. And what they find is it's actually because of nuclear changes in the Earth. Just like helium, the alpha particles bubble up to the surface, the radon bubbles up to the surface. And if you've got it's over certain kind of rock formations, it's more common because there's that kind of rock down below. And if it gets up to the surface, it's actually denser than air. So it fills up your basement. So it becomes concentrated in low-lying areas. So if they find out you have a radon problem, all you do is put an air changer in. So it pumps that radon outside and gets the alpha particles outside where it's not going to hurt anybody. Make sense? Okay, so we got to look for radon because radon's an alpha producer, and you can't you can't smell it, you can't taste it. It's colorless, odorless, but it gives you a chance of getting cancer every time you breathe it. Okay. Second kind of particles, beta. Beta are small, so they're less likely to run into things, and they're charged, so they are going to be affected by the charges inside the things you're shooting them at. Since they're much smaller, they're less likely to run into things. So the atoms have to be denser for it to work. Okay. So beta is stopped by aluminum foil. If you get it thick enough. It says aluminum. Aluminum foil is not quite thick enough. You got to get layers of aluminum before it stops. The more layers you get, the better it does at stopping it. But it's going to cause the same kind of problems that alpha does if it hits cells in the same way. Except this gets to go through more cells. It's not going to be stopped by your skin. So it could hit your lymph nodes. It could hit your organ tissues. Okay? It could hit your bones, and if it could hit your bones, it might hit the marrow inside, and the marrow is where all the blood cells are made. That's how you get leukemia. Leukemia is just cancer of the blood. Okay? So it caused bone cancer, organ cancers, and bone cancer, osteocancer is just the bone not growing right, and then the marrow grows wrong, then you get leukemia because your blood cells are made in the bone marrow. Gamma. Well, gamma has no charge and no mass. So it gets past everything. It's the most penetrating, by far. It will go through feet of concrete, inches of lead. It's hard to stop. It is very high energy. It is very dangerous. It can cause cancer anywhere. And it's why we're going to have trouble sending men to the moon, men to Mars. Okay? You want to send men to Mars, they got to fly through space. The sun is constantly giving off alpha, beta, and gamma, and all sorts of particles are flying off the sun. On Earth, we're protected because the Earth has a magnetic field. And it puts an ionosphere around the Earth that makes all those charged particles go around us. Okay? But when you're flying between the Earth and Mars, you leave the Earth's magnetic field. So there's nothing protecting you. And you get pounded by gamma rays the entire way to Mars. Once you get to Mars, Mars' magnetic field is collapsed. It doesn't have a magnetic field anymore. So you're going to get pounded with gamma rays while you're on Mars. And then all the way back, you get pounded by gamma rays. Okay? It's a problem. Okay? They can't figure out how to keep people alive that long with that much gamma ray hitting them.
We already tried.
We've simulated it with animals, but we've never tried to send man to Mars. Okay? The moon is still inside the Earth's protection. So the moon is still close enough to be inside that protective field. So we've never had to send, we sent probes out there. We can measure how much is hitting. The question is, how do you shield the spacecraft? Because what do? Make it out of feet of concrete? Is that going to be an effective way to make a spacecraft? No. So that's the challenge. How do you keep the gamma radiation from cooking you on your way to Mars and back? And once you get there and come back. So because it's going to be 2 years. Okay? Because Mars comes closest to Earth every 2 years, about right around every 2 years. So you take off when it's getting close, so you make the shortest trip, and then you stay on Mars so you can fly back with the shortest trip too. So it's about a 2-year commitment to be pounded by gamma rays. That's a problem. Okay. So I found a couple of simple little simulations that show you those things. Yeah. So the 3 kinds. Alpha, you shoot alpha. Actually, alpha's the problem is you got to do it. This is what Rutherford used, and he had to take the air out of the container. Air is molecule, is atoms, right? Air would stop alpha particles. They'll bounce off of it. Okay, beta goes through. Paper will stop by aluminum, and gamma, and partially absorbed by lead, a little bit absorbed by lead. Okay. So, if you're inside the cell, and an alpha decay happens inside the cell, it has to be absorbed inside the cell. It's going to be absorbed before it leaves that cell. So if you can get something into your body and it goes into the cell and then it does alpha decay, it's much more dangerous than alpha decay outside your body. Outside your body, everything's going to stop it. Okay? What happens inside the cell, the only thing that's going to stop it is something inside that cell. Okay? So this the place I remember this one is polonium-210. The Russians used polonium-210 to kill a former spy. They met up with him, had a little tea. They added something extra to his tea, polonium-210, and then he walked away. And he felt sick later that day. And he felt really sick, so he went to the hospital, and they found that cells throughout his entire body were dying because he did polonium-210. And wherever it falls apart, it kills those cells. So that's radiation sickness, is just random cells being killed off in your body. And eventually your body shuts down and you die. Yeah.
Where do we find gamma radiation on Earth?
We're being hit by it occasionally, okay? But you have to be around something nuclear, and it got to be some pretty high, got to be some. It's going to be pretty protected. You're not going to see it very often, and you'll never see it. I mean, you're getting hit by gamma radiation a little bit right now. You can't tell. There's always some background radiation. Yeah.
So if we blew up a nuke, that would release like gamma radiation.
That would lead off gamma radiation and a whole bunch of radioactive particles that were going to decay later. So if you ate them, they're going to decay inside your body. So the damage is not just from the blast. That's what the radioactive fallout does, is you eat it, and it does alpha decay inside your body. And it's got to kill whatever cell it's in.
How far would that go, like the
Well, actually, the Bureau of Atomic Scientists has put up a website that actually shows you how you pick a modern weapon, you pick where you live, it'll show you how big a hole it'll blow in the ground. Yeah, it's a big hole. But they don't talk about the people dying from radiation for years later, or the fact you put up so much soot in the air that the sun can't get through, and we go through something called a nuclear winter. Nuclear winter, the sun can't get through, the earth gets cold. Plants don't grow. Okay. Now, outside your body, what does beta do? Beta is going to can get outside the cell. So it doesn't have to, it won't be absorbed inside the cell, be absorbed by, but it's not quite as dangerous inside as alpha. Alpha is going to be absorbed before it leaves, right? Because they can't get out. Beta has a possibility of getting out, and gamma is coming out for sure, right? Gamma's coming out. So these aren't going to have the concentrated problems that alpha is, because a lot of their energy can get out. Alpha's got to be absorbed inside your body. So alpha at your skin. Oh, first of all, living skin cells on the outside, dead skin cells are on the inside. Okay? It's kind of strange that your skin grows inward. Okay? But the alpha particles can hit those living cells, but that's as far as they're going. The beta will get through the living cells and it's absorbed in the organs, and the gamma, it'll just keep going. It might, if it hits a cell, it might do it. Just, it doesn't necessarily get absorbed in your body. Okay, so there it is in words. Let's see if we can find it in practice. Okay. So, up here I have a Geiger counter. Okay. And when it finds something radioactive, it beeps. So every one of those beeps you hear is it detecting a radioactive particle. Okay. There's always a few radioactive particles around us. Okay. So this is called background radiation. Okay. So, yeah, there it is. So here I have some cobalt-60. it's a little bit more radioactive than background. Okay. Here's some strontium-90. It's radioactive too, right? So let's try to figure out what kind of radiation it is. So I've got my strontium-90. If I put a piece of paper between them, if I can find it. Piece of paper make much of a difference? No, it's through. How about something a little thicker? I couldn't find a piece of aluminum, so I found some copper instead. Put in the right spot? Piece of copper worked pretty well. Compare that to the cobalt 60. Cobalt 60. Aluminum doesn't make much of a difference. Copper doesn't make much of a difference. So see the difference between those two? Okay. And then finally, get some lead. Okay. If I put a layer of lead over it, cobalt 60 comes through the lead. It's a little slower. I put more lead, it blocks more. So what do you think what kind of particles in cobalt 60? Gamma. And in the strontium-90? Beta. And I have some polonium-210 here, which is an alpha emitter, but it doesn't work. Okay? It doesn't pick up any more than background. Why? Because polonium-210 has a half-life of 138 days. I bought it in September of 2016. So there's been 1,000 days, and it's only 138 days for every half-life, so I'm about 8 half-lives. So I'm 1/2 to the 8th power times my original amount. Well, 1/2 to the 8th power is 1/256th. So it actually has dropped so low we can't tell from background, yeah.
So elements become safer as time goes on.
Yeah, eventually, yeah. Yeah, most of the ones that are above 83, when they decompose and they hit lead. You remember that in your reading it said lead was one of those magic numbers that was stable. So once you get to lead, you can be stable. So lots of things decay until they become lead and they stop right there. Okay, question?
How many protons do elements become radioactive?
Well, in general, there's going to be radioactive forms of all of them. Okay, does that make sense? You get the wrong ratio of neutrons to protons. But above 92, there are no stable elements. Okay, does that make sense? Because the ratio doesn't work right. Okay, the ratio doesn't work right. At 43, and it works out that number cannot be held together with neutrons. But you can't get the right ratio, so the neutrons will stay. So you can't find it in nature. Okay? And promethium, I know about that. Promethium is, again, it's a big atom, so I would suspect that we can't get that ratio. But so, everybody okay with the danger of it? Okay, what we got to do about it? Okay. Actually, we haven't talked about the real usefulness. Why would anybody do this outside of being able to penetrate stuff? Okay. Well, the way we use it, the nuclear change we use most often for power, right, the one we use for power is fission. Okay. Okay. The splitting of a nucleus into 2 smaller atoms. Now they say, "Whoa, isn't that what alpha decay is? you get a smaller atom and then a helium. No, we're talking about two significantly big atoms, two atoms bigger than helium. Okay. Oftentimes it started by the capture of a slow-moving neutron. So a neutron flying through, if it's flying through, it's not going to be repelled or attracted to the nucleus, but if it runs into a nucleus and gets close enough, that strong force comes into play, and it makes a new isotope, and that isotope is going to have a different ratio. That new ratio might be unstable. Okay? For the first one we controlled successfully, you took uranium-235 and shot a neutron at it, you could make uranium-236. And uranium-236 is unstable. So uranium-236 falls apart and makes two big atoms. It makes a krypton atom, a barium atom, and 3 more neutrons. Krypton's a real gas. But it's a gas. You're not going to make a mineral out of it, so there's going to be no kryptonite. Okay, now, this is just a sample of the kind of big atoms that might fall off. It might fall apart into. Yeah.
Why don't noble gases have liquid or solid?
Because they can't attract themselves well. We'll talk about what forces have, and they do have liquid forms. You can make xenon in a liquid. All you got to get it down to is 165 Kelvin, which is about negative 100 degrees Celsius, negative 100 Celsius. And radon will be a liquid at negative 180 Celsius. It's cold, but you can get it there. It's not as cold as liquid helium, which is, I think, 4. Yeah, 4. You see those truckloads of it going down the road. You see those gas trucks. Oftentimes they're carrying carbon dioxide or oxygen, but if you see the skinnier ones are hauling liquid helium, probably out to Vandenberg, because they use it in some of the things they send up into space. Okay. So I start off with a little neutron capture. That new one's unstable. It falls apart into big pieces. And actually, the key to this whole process is that I only put in 1 neutron, and I get 3 out. Okay. So the neutron hits uranium-235. It makes 2 lighter elements and more neutrons. Those neutrons hit other uranium-235s. And they fall apart into atoms and make more neutrons. But I started off with 1 neutron. The first time I get 3 out, so I can hit 3 more atoms. And then I can hit 3 more atoms, so I'm up at 9. Then those neutrons hit, now I'm at 27. And then those hit, and I'm at 81. And then those hit, I'm at 243. And those hit, I'm at 729. The numbers start getting big pretty fast, right? So you get a chain reaction. The neutrons produced in one atom, start the reaction in other atoms. So the energy in the transformation of uranium-235 when it does this, if you used a kilogram of uranium-235, it would give you as much energy as blowing up 20,000 tons of dynamite. 20,000 tons of TNT. So 1 kilogram, 2.5 pounds. You can hold it in your hand. When that goes off, it has the explosive power of 20 kilotons, is how we'd say it. So a simple demonstration somebody showed me, but it's really pretty cool. This is a table with mouse traps on it. all set. One. That is a chain reaction. Okay. Okay, that's a chain reaction. The first one didn't set it off, but the second one set off one, which set off the others, which set off. Well, the first one failed because the extra piece didn't hit another mousetrap. So the issue is, not only are you going to make those 3 neutrons, you have to make those 3 neutrons hit another atom. Okay? You got to have domino. If you take out the middle domino, the dominoes stop working. Well, the same idea here is you've got to get the neutrons to hit another atom. And it turns out that you have to get it so that the average is just bigger than 1 on average hits it. So let's open it up here. So here we go. Okay, so I fire a neutron. It gives it more energy. Okay. It's not stable, and it falls apart into pieces. Oops. And see the 3 neutrons. So if I have just 1, it doesn't do much, but I can add some more. So let's put about 12 of them in. They're all going to miss. So 12, it didn't hit anything, so that doesn't do any good. Oh, it hits 1, it's another. But it fizzled because not all of them, I averaged less than 1 hitting. So what I need is I need more of these, right? There's got to be a certain number so that I can guarantee they're going to hit. So it's about how close together the atoms are, how concentrated they are, how many are nearby to hit. That determines whether you're going to have a chain reaction or not. That make sense? Okay. So that's what determines whether you're going to have a chain reaction. Okay. Oops, where I saw this. The first one didn't work. So the whole thing is to keep it at, keep it right at the right number. Now, talk about it in terms of a bomb. What they do is they put in something that absorbs neutrons. Control rods absorb neutrons. So if I fire a neutron in here, it can't go past the control rod until it gets stuck. But if I pull the control rod out and fire it, it soon goes out of control and my reactor blows up. But if I put the control rods in, I can quash it by absorbing the extra neutrons. So they put in stuff that absorbs the neutrons so they can control, and they want to run a reactor where the neutrons hitting is exactly 1. Anything over 1 is going to go out of control. Anything under 1 is going to stop. So you want to keep the balance at exactly 1. So Chernobyl, here's what they did. They said, what if we wanted to start our reactor really fast? We would pull the control rods out and fire our neutrons in, and then once it got going the way we want it, we would just slide the control rods in and get it controllable, so we get just a constant set of power. That was their plan. Okay? So they're running an experiment late at night. It was about how fast they could spool up the reactor, how fast they could get it hot. So they pulled the control rods out, fired the neutrons. It started going, so they went to go push the control rods in, and they wouldn't fit because it had gotten hot and it got out of control. It got hot so the control rods wouldn't fit. You can't put the control rods in. It goes out of control. It melts the uranium. The uranium pours down to the bottom. Luckily, there was a wall at the bottom, and part of it fell on one side of the wall, and part of it fell on the other side of the wall, because all you need to make this happen is enough stuff in the same room. But because it fell into 2 piles, It wasn't critical anymore. And we got lucky. All we have is a place that's going to be deadly poisonous for the next couple 100,000 years. Okay. Oh, that's bad, by the way. We want to watch it blow up. It actually doesn't blow up, I don't think. Oh, it just. But you can tell from the numbers. You do over here. You would not want to be here. Boom. Okay. So, it is scary. So we need to be able to control that stuff. Okay. The opposite of fission is fusion. Instead of one big atom falling apart into two smaller atoms are put together to make a heavier atom. A couple of isotopes of hydrogen, hydrogen 1, hydrogen 2, and hydrogen 3. You slam them together, you make helium. And a neutron comes flying out. Yep, there's always background radiation going on. Okay. This change right here gives you much, much more energy than fission. Much, much more. The problem is you've got to get protons to hit each other. You've got to get positive pieces to hit each other. And that means they got to be moving really fast in order to do it. So you got to get up to like 1,000,000 degrees. You know, actually a million might do it. Probably hotter. Yeah, yeah. They've done it here on Earth. But right now, currently it's happening all the time. All you gotta do is look up and see, because this is where the sun gets its energy.
How hot is lava?
Lava's in the 3,000, 4,000 degree. Okay. So the problem is, it gives you a lot of energy. So when they wanted to make a bigger bomb than an atom bomb, they put this stuff inside an atom bomb. Okay? Because it'll be 1,000,000 degrees in there. And then they called it the hydrogen bomb, because the hydrogen bomb used the atom bomb to start the fusion of the hydrogen inside. And when they drop atomic bombs, they come in two categories. Atomic bombs are measured in kilotons, how many thousands of tons of TNT they replace. Hydrogen bombs are measured in megatons, how many millions of tons of TNT they replace.
So how many is like a hydrogen bomb?
Hydrogen bombs are in they're up to the 10 or 20 megaton. I think the biggest one ever built, Russia built one, I think that Cobalt 60 bomb, I think it was like 65 megatons.
We're all gonna die.
Oh yeah, this will kill us all. Just so you know, this is what I grew up in. I grew up on a military base. My girlfriend's father was in charge of the maintenance on cruise missiles. That was his job. Okay, so this is what I grew up around. And so when they talk about you guys grew up around phones, we grew up around the idea that we were going to die because the Russians were going to kill us. That's how I grew up. Okay, so transmutation. Trans means across, mutation means to change. Transmutation is just a way of artificially changing what kind of atom you have. So you bombard the atom with particles. The easiest one is neutrons. You shoot neutrons at it. And you can make a new isotope of that neutrons. Sometimes that new isotope is unstable, though, when it falls apart on you. This accidentally happens in nuclear reactors. So all the metals that you make up a nuclear reactor with, after a few years, are not all made of the same metal they started with. The metal goes bad because it gets changed into, it's not iron anymore. It's changed to something else. It's not going to be as strong as iron. It's not going to hook the way iron does. And your building gets weaker over time. So you got to engineer all that into it too. The protons and other charged pieces are repelled. They need a whole bunch of energy before they're going to be able to connect. So what they do is they use a particle accelerator. The first ones were linear. You just got a charged piece and you shot them into each other. Now they make them in big circles so that they can spin them and get them going faster and faster. There's one in Chicago called Fermilab. That was the big one for a while. And they get charged atoms moving in separate directions around these rings, and then they slam them into each other. So if you want to make element number 108, you slam something where the protons would add up to 108. And you try to slam those two pieces together. We don't have, that's because this periodic table was bought when I started teaching here, which was 1993, and they hadn't made 108. Right now they've made everything up to 118, okay, by slamming atoms together. Okay. Everything bigger than 92 was made this way. Now usually the things you have half-lives of fractions of a second, and you only make one or two of them, one or two atoms. So you don't actually look for the atom you were trying to make, you look for what that atom would decay into, that nothing else would decay into.
What's going to happen when we get to element 119? Like, is that just going to start?
No, it's just going to be the next one. The interesting thing, they think if you get up to near 150, atoms will start being stable again. That there's another magic number that happens near 150, if you can get them that heavy.
So everything over 92 basically
We made. Yeah, so the americium in your smoke detector came from a nuclear reactor. They put some stuff in a nuclear reactor, turned it into americium, put it in your smoke detector. None of it's natural. Because it all has half-lives that are shorter than the age of the Earth, much shorter. So if there was any made, fact is, where did it all come from? Where did all those elements come from? Well, fusion. Okay, so you get hydrogen that slams into each other, makes helium. That gives energy to the sun. But eventually you're going to run out of hydrogen. And then the heliums and the hydrogens are going to run into each other and make lithium. And two heliums can run into each other and make beryllium. Okay? And it gets, but you got to get them getting hotter and hotter. The star's got to get hotter and hotter to keep doing this. So every element heavier than hydrogen got made in the center of the sun, a star. And you can make everything up through iron in a star. But that's as far as you can go. It's not enough energy to make anything heavier than iron in a star until it blows up. Everything heavier than iron was made in a star explosion, a supernova. So you got a whole bunch of things heavier than iron inside of you. You're made of stardust.
How come diamonds aren't an element?
What?
How come diamond isn't an element?
It's carbon. It is an element. It's carbon, pure carbon. Okay, we'll talk more about diamonds when we talk about what the structure is. So, how to build a bomb?
Gold is an element.
Yeah.
Wasn't maybe made for a bigger element like when we make gold?
Well, they can. They have artificially made gold, but it costs more money to make the gold than the gold is worth. There. Does that make sense?
Yeah.
They can. Actually, what? Hey, cameras. So they can make, but it's really expensive because you've got to use a lot of energy to get those positive pieces flying into each other. I mean, because think about it. If you made gold, it's number 79. That means you got to put at least something with a positive 40 charge in there, and you got to get something else with a positive charge to get close to it. So that's not going to be easy to do. Okay, and that means you got to get really, really high speeds. I mean, approaching the speed of light speeds when they start slamming into each other. Well, it makes stardust too. It's the remnants of stardust as well. Okay, everything heavier than hydrogen. The hydrogen came with the Big Bang. Okay, so to make a bomb, put enough uranium or plutonium in a sealed container and it will blow up. That's it. That's all you have to do. Just put it in a sealed container. Okay, that 22 kilograms is called the critical mass. And that's where you have just enough of those atoms close to each other that that the neutrons are going to hit. Remember how that we had to make sure the uranium-235s were close to each other in order for the chain reaction to work. Well, if you got 22 kilograms of uranium, you've got them close enough together. They're going to hit. The average is over 1, so all you do is close the door and it gets out of control. Okay? So the first atomic weapon dropped in anger was actually just a 55 caliber howitzer with a slug made of uranium and a target, a ball made of uranium. And they were separate as the bomb fell. And then just before it got to the ground, they triggered the gun, shot the uranium into the uranium. Now I've got critical mass, and it blows up. That's how you blew up the first one. Okay. The second one is instead of getting enough stuff, you can use less stuff if you just get it closer together. So the first bomb they blew up and the one they dropped on Nagasaki was a plutonium bomb. And the plutonium bombs, they took the core and surrounded it with shaped explosives that were all designed to blow inward. And they all had to blow at exactly the same time. So they blow at exactly the same time, all the pressure's inward, and that plutonium ball will actually get smaller. You can compress a metal if you've got enough explosives. And once it gets smaller, they're closer together. The neutrons are all going to hit, and it blows up. So instead of getting enough pieces, I can just make those pieces closer together by compressing it. Now the hard part, getting the uranium or the plutonium. Because you have to separate it based on the fact that the only difference is it weighs 1% less than uranium-238. Because when you dig uranium out of the ground, 99% of it is uranium-238. Only 1% is uranium-235. So you got to separate that uranium-235 from the 238. That process is called enrichment. And that's what we're trying to stop Iran from doing right now, enriching the uranium. Because to get to a reactor, you only need to get about 4% uranium-235. But to build a bomb, you need much higher percentages. So if you go above 4, there's only one reason to go above 4. And that's to go as close to 100 as you can so you can make yourself a bomb. Yeah. Hey, there's nasty stuff out there in the world. Okay, second part. Hard part is getting the explosions to all happen at the same time. Because they got to happen at exactly the same time. Because if one's late, the ball of metal will be pushed to the side. It won't be squeezed. Oh, no. Fractions of milliseconds. Okay. So the things we don't sell, the things we don't sell to countries that are trying to build bombs are really good timers. Like the timer for a strobe flash for a high-speed photography, we don't sell those to Iran because the timer that does that high-speed strobe could also control those reactions so that those explosions, they all happen in the right amount of time. That you use as a timer for that. So we don't sell them those pieces. Okay, that's the idea. Okay, so that's the issue is, now if you just put that 22 kilograms in, it'll blow up, but it'll blow itself apart pretty easily. So it's going to spray radioactive material all over the place, and it'll probably fizzle out. And that's what they call a dirty bomb. Because it doesn't make as big an explosion, but it sprays radioactive material everywhere. Yeah, you can. So, but it's hard. You got to find it alpha decay by alpha decay, and you got to take. It's going to be dust. So, these instructions for things like recovering from a nuclear war tell you to take the top 3 inches of soil off the ground, and put it into a pile and mark it as dangerous, and then you can farm everything underneath that. Right now they use lead materials and thick concrete. The question is, where do you store it? Because it's going to be radioactive for a few million years. The U.S. answer is we planned Nevada, but people voted against it. We planned on a place in Nevada, but people voted against it. So we have no place to store it. Yeah, question?
How do humans find a way to weaponize everything?
Because we like to eat animals. We're scavengers. We're tool makers, and the two go together really well.